Now this little element, I should probably explain. This sort of funny looking curvy e, it just means in. So this says that if x is in the set negative infinity to 1, and it's open on 1. And so if we look over here, we're talking about which part of the diagram? We're talking about the part from here and leftwards. So as x is increasing, y is decreasing, right? So if y is decreasing as x increases, then the slope must be negative. And we could see that if we drew a tangent line over here. This tangent line is negative. Or I should say, that doesn't make a lot of sense, it has a negative slope. Has a negative slope, this tangent line right here. And if we take a closer look down here, what happens when this function is equal to 1? Well, we've got a tangent with slope equal to 0. So f prime 1 is going to be equal to 0, right? The derivative when x is equal to 1 is equal to 0. Now, it's constant, right? So this means that it's constant. The rate of change is 0. The rate of change in y as x is changing is 0 at that point. But that's okay, because f of x is less than 0. We've got a round bracket here, and so it excludes 1. It means we can get really, really close to 1. But x here is never going to be equal to 1. And so number 1 is true. So number 1 is true. Now I'm going to clear off some of this. And let's take a look at number 2. So it says that the derivative, or the slope, of the line is positive if x is on the element 1.5 to 2.5. So we're looking at the interval here. This interval I between these 2 points. And it looks to me like this is true. So 2 is true as well. On this interval, on the interval where x is greater than 1/2 and less than 2.5, y, or f of x, is increasing. F of x is increasing. So it's true. Now what about number 3? So it says that f prime of x is increasing, strictly increasing, between 1 and all the way to negative, or to positive infinity. Well, we can see that along here, the function is increasing. But again, we get this flat point when the function hits a peak. It hits what we'll later call a local minimum, or sorry, excuse me, a local maximum. And then it's going down. And so we can see that it's equal to 0 here. That's f prime. And that's when x is equal to 3. And so this is definitely false, because it also includes all this space out here. And what about number 4? F prime of x is strictly greater than 0 if x is between 1 and 3. So we're looking at this space here. It definitely looks like it's increasing, but notice that we've got closed sets. And so a closed set includes, in this case it includes 1 and 3, and we can see I haven't drawn them really perfectly. But we know that f of 1 is equal to 0. We know f of 3 is equal to 0. And so this has to be false. We could make it true by saying that the function f is increasing. But f prime x is not strictly increasing on the interval from 1 to 3. It's constant, or it's equal to 0 when x is equal to 1 or x is equal to 3. Here's another problem for you to try, and I'll give you the solution. We can walk through it together. Use the Newton quotient and the limit to find the derivative of 3x squared. And so press pause on your video, and then when you unpause, we can go over it together. But give it a try on your own first. Let's start off by writing out our limit. As h approaches 0, we're going to have 3, I'll use a plus h squared minus 3a squared, all that divided by h. And if I work out that bracket, I'm going to have 3 times a squared plus 2ah plus h squared minus 3a squared all over h. And I'll write out the limit because I don't want to forget about it. And maybe if I jump just a little bit, I'll have 6ah. And you can see that this of 6ah plus 3h squared over h. So that's going to cancel out with this thing there. And then the 3 comes in and multiplies the 2 remaining terms. I can simplify this as 6a plus 3h, right? Getting rid of that, that, and that. And then now if I'm going to take the limit as h goes to 0, we're going to be left with 6a plus 0. So we just have 6a, which is the derivative of f.